When the basketball moves, the main camera follows and shoots. If you were asked to design and implement it, what would you do? My strategy is to always fix the camera at the position above and behind the basketball. How do I know where this position is more suitable? We have already adjusted it before. We can record the position of the main camera and the position of the basketball at the beginning of the game. Then we can calculate the offset vector of the camera relative to the basketball. Of course, you can also use the configuration file to record these data later. Then read it from the configuration file when the game is loaded. Now, let's write a script to control the main camera. Create a new TypeScript file in the scripts folder. Name it Camera Controller. Mount it to the main camera node. Double-click to open. Add a configuration to set the target for the camera to follow. Select the camera node. In the inspector window on the right, the associated tracking object is basketball. Declare a variable to record the offset vector of the camera relative to the tracking object. Calculate the value of the offset vector in the onStart method. Then update the position of the camera in the onLatUpdate method. Make the position of the camera always at the offset vector of the object being followed. Some students may wonder why LatUpdate use it here instead of an update. Here I'll give you a brief explanation. In terms of execution order, the update function is called first when each from is updated. The LatUpdate function is called after all update functions are executed. This means that if you use CTA functions in multiple scripts, the LatUpdate function will wait until all update functions are executed before starting to execute. In terms of usage, since the update function is called when each from is rendered, it is suitable for handling operations that require real-time updates, such as input, movement, rotation, animation, etc. The LatUpdate function is suitable for calling after all update functions are executed. It is usually used to handle operations that don't require immediate updates, such as camera following, perspective updates, etc. This distinction can help avoid jitter inconsistency problems caused by updating multiple systems at the same time. Of course, students know how to learn must be good at using search engines. You can find answers to any problems you encounter through search engines. Ctrl+S, save the code. Then run, and test the camera tracking effect. We found that the camera tracking effect is okay when moving with the ball. However, when shooting, the basketball has a large and frequent up and down vibration, which will cause the picture to shake. It is easy to cause dizziness to the player. How to solve this problem? We use interpolation to adjust the position of the camera. To avoid hard coding here, we set a position interpolation coefficient. It is convenient to adjust through the editor when testing later. Display the game window and the scene window side by side in the editor. Run and test. You will find that the picture is not as shaky as at the beginning. And the smaller the interpolation coefficient, the more stable the picture and the smaller the shaking. It's like using a shock absorber. What is the reason and principle? Let's explain it to you. When interpolation is not used, since the position of the camera is always the position of the object being followed plus the offset, if the object being followed shakes significantly, the camera will definitely shake significantly. When interpolation is used, how does it deal with it? During the learning process, you can check our API for any questions. For example, here we can search for vector 3, then find the lerp method. Or you can search for lerp directly. Click in and you can see the parameter explanation and sample code. To prevent some students from not understanding, I have drawn a few schematic diagrams for you in advance. The first parameter of the lerp interpolation method is the starting vector, and the second parameter is the ending vector. The third parameter is the interpolation coefficient. The first parameter, in our code, is the position of the basketball, and the second parameter is the position where the camera is expected to appear. When the interpolation coefficient t equals 1, the result of the interpolation is the ending vector, which is the position of the offset we set, so the effect is the same as if interpolation is not used. If you don't believe it, we will adjust the interpolation parameter to 1 and run it for everyone to see. Everyone pays attention to the scene window. The relative position and relative distance between the camera and the basketball have never changed. On the other hand, what will happen when the interpolation coefficient t is 0? At this time, everyone pays attention to the scene window and finds that the camera position remains unchanged. Students who have questions can copy the sample code in our API after class and test and verify it. Just like this, save and test. During the running process, we adjust the interpolation coefficient. Observe the effect. Everyone pays attention to the relative position of the camera and basketball in the sense window, and the shaking amplitude of the game window screen. It is found that the closer the interpolation coefficient is to 1, the tighter the camera follows when the object moves. It is found that the closer the interpolation coefficient is to 0, the smaller the screen shakes. However, when we move the basketball, everyone will find a problem. Sometimes you can see the whole picture of the basketball, and sometimes you can't see the basketball. When you see the whole picture of the basketball, do we still have to be a protagonist to be rigorous? Therefore, the strategy we adopt here is to interpolate the camera position only when shooting. In other cases, the previous processing method is still used. Therefore, we need to determine whether interpolation is needed based on the state of the basketball. First, declare a member variable basketball controller to get the control script on the basketball node. The purpose is to get the basketball status. Then initialize its value in the onStart method. In the onLatUpdate method, different methods are used to update the camera position according to the status of the basketball. If the basketball is in flight, use interpolation calculation. Otherwise, just use the previous method. Save and run. The camera follows normally when moving and shooting. However, there is a small problem that we need to fix. When the force is too large, the basketball is thrown out of the court, causing the test to be unable to continue, which is not convenient for us to debug. We right-click the previous ground node ground, and choose to create a new plane. Change its Y value to -0.01. Adjust the scale value to be large enough so that no matter how strong the shot is, it can fall into this plane. Change its color. Add a collision body. Set the level to holder. Test. No matter how strong the shot is, the basketball will not fall into the void.